Observational astronomy is the empirical foundation of all astrophysics, for because the universe cannot be experimented upon, almost everything we know of stars, galaxies, and the cosmos is inferred from the radiation that reaches our detectors on Earth and in space. Astronomical brightness is reported on the magnitude scale, a logarithmic system inherited from the Greek astronomer Hipparchus, who ranked the naked eye stars from the first magnitude, the brightest, down to the sixth, the faintest. In 1856, Norman Pogson formalized the scale by noting that a first magnitude star is about 100 times brighter than a sixth magnitude one, so that a difference of 5 magnitudes corresponds exactly to a factor of 100 in brightness, and a single step of 1 magnitude to a factor of about 2.5. A minus sign in the defining relation preserves the ancient convention that brighter objects carry smaller, and even negative, numbers. The Sun sits at about -27, the full moon near -13, the brightest star Sirius at -1.5, and the faintest stars the unaided eye can see at around +6. To turn a relative brightness into an absolute statement, one must fix a 0 point, the magnitude of a hypothetical source producing exactly 1 count per second on the detector. 2 conventions dominate. The Vega system sets the magnitude of the bright star Vega to roughly 0 in all the classic bands, so that a star's color measures how its spectrum differs from Vega's. The AB system instead ties the magnitudes directly to physical units of flux, anchoring them to an absolute standard rather than to a single calibrating star, which is why most modern surveys report their magnitudes in the AB system. Apparent magnitude measures how bright an object appears in our sky. Absolute magnitude measures its true, intrinsic luminosity, defined as the apparent magnitude it would show if placed at a standard distance of 10 parsecs. The two are linked by the distance modulus, the simple difference between them, which grows by 5 magnitudes for every factor of 10 in distance, a direct consequence of the inverse square dimming of light. A star of apparent magnitude 15 whose absolute magnitude is known to be 5, a sun-like star, has a distance modulus of 10, which places it at 1,000 parsecs. Applied to standard candles of known intrinsic brightness, the Cepheid variables, the RR Lyrae stars, and the Type 1a supernova, this same reasoning is how distances are measured far beyond the reach of any direct geometry, which makes the distance modulus one of the most used relations in all of astronomy. 2 refinements matter in practice. First, an apparent magnitude is always measured through some particular filter or bandpass, so that a single star has many apparent magnitudes. The bolometric magnitude, which integrates the light across all wavelengths at once, is the one that enters a true luminosity. Second, interstellar dust both dims and reddens the light passing through it, so the observed magnitude carries an extinction term that must be subtracted before any distance is inferred, and failing to correct for it makes objects appear systematically further away than they are. These corrections connect the simple bookkeeping of magnitudes to the calibrated photometry that is the working core of the subject. Photometry is the calibrated measurement of an object's flux within a defined band of wavelengths. Since the 1980s, the charge-coupled device, or CCD, has been the dominant optical detector, having replaced the old photographic plates for its high efficiency, its linearity, and its digital output. It is a grid of silicon pixels in which each incoming photon above a threshold energy frees an electron and the accumulated charge is then read out and digitized. The rate at which a telescope gathers photons scales with its collecting area, and therefore with the square of the diameter of its aperture, so that a 10-meter telescope collects some 10,000 times more light than a 10-centimeter amateur instrument. This is precisely why aperture, and not magnification, is the defining specification of a research telescope. The scale of the image on the detector is set by the focal length, and good practice is to sample that image so that the blur of a star spans about 2 pixels, the criterion named for Nyquist, since any coarser sampling throws away resolution, while any much finer sampling spreads each photon across more pixels and merely adds noise for no gain. The quantum efficiency of a detector is the fraction of the photons falling on it that are actually converted to detected electrons, and modern thinned CCDs achieve above 90% across much of the optical range. Choosing the image scale to match the expected size of the star is thus a fundamental design decision, one that couples together the optics, the detector, and the noise budget of every exposure. Raw frames from a CCD are not yet science data. They must first be cleaned of 3 instrumental signatures using calibration frames. A bias frame, a readout of 0 seconds, records the electronic offset added to keep every pixel value positive. A dark frame, a long exposure with the shutter closed, records the thermally generated dark current, which is the reason science detectors are cooled far below freezing to suppress it. And a flat field, an image of a uniformly lit surface, maps the pixel-to-pixel variations in sensitivity, the dust shadows and the vignetting, all of which are removed by dividing the science frame through by it. With calibrated frames in hand, a star's flux is then extracted either by aperture, photometry, summing the counts within a circle drawn around the star, and subtracting the sky measured in a surrounding ring, or, in a crowded field, by fitting a model of the instrument's own blur profile to each of the overlapping stars. Every measurement, though, is limited by noise, and the signal-to-noise ratio is the single most important figure of merit in the whole of observational astronomy, measuring how confidently a real signal can be told apart from the random fluctuations that always accompany it. A source is conventionally called detected only at the 5 sigma level. The dominant noise in optical work is photon shot noise. Because photons arrive at random, the noise upon account of some number of detected photons is simply the square root of that number, an irreducible fact, a property of light itself and not of any instrument. To this must be added the shot noise of the sky background, the shot noise of the dark current, and the read noise of the amplifier, which alone among them is added just once at readout, and does not grow with the length of the exposure. Combined together in quadrature, these terms give the canonical equation that governs the noise of every image a CCD records. 2 limiting regimes are worth understanding. In the bright, source-limited regime, the star's own shot noise dominates, and the signal-to-noise grows only as the square root of the star's counts, and since those counts grow with the exposure time, the signal-to-noise grows only as the square root of the time, so that doubling it demands 4 times the exposure. In the faint, background-limited regime, the sky or the read noise dominates instead, and a bright sky then heavily penalizes faint work, which is exactly why the deepest imaging is done at dark sites, on moonless nights, and from space. A concrete consequence is that reaching just 1 magnitude fainter, at a fixed signal-to-noise, takes about 6 times the integration. These calculations, run before observing on an exposure time calculator, are how an astronomer decides whether a target is even reachable, what filter and exposure to use, and how many frames to stack, and they define the limiting magnitude that drives the entire economics of survey design. Spectroscopy disperses light into its constituent wavelengths, transforming a single point of light into a spectrum whose bright and dark lines encode a star's composition, temperature, density, gravity, magnetic field, and motion. It is the single most information-rich technique in all of astrophysics. It was Fraunhofer's catalogue of the dark lines in the solar spectrum, and Kirchhoff and Bunsen's identification of those lines with particular chemical elements that founded the discipline of astrophysics itself by proving that the stars are built from the same elements as the Earth. A modern spectrograph disperses light with a diffraction grating, a surface ruled with many fine parallel grooves, at which different wavelengths interfere constructively at different angles and so are spread out across the detector. The HL designs pack many high orders of the grating onto one detector at once, winning very high resolution together with broad coverage in a single exposure. The defining performance metric of a spectrograph is its resolving power, the wavelength divided by the smallest interval of wavelength it can separate, and this carries a direct interpretation in velocity, since the smallest velocity difference it can distinguish is roughly the speed of light divided by that resolving power. A resolving power of 50,000 can resolve motions down to about 6 kilometers per second, and one of 100,000 down to about 3. Low resolving power is enough to classify galaxies and to measure their redshifts, but high resolving power is needed to resolve the detailed shapes of stellar lines, to measure chemical abundances, and to detect the subtlest Doppler shifts. There is a fundamental trade at work, for a higher resolving power spreads the same photons across more pixels, lowering the flux in each and demanding a longer exposure or a larger telescope, so that resolution is forever balanced against signal-to-noise. What a well-resolved spectrum reveals reaches far beyond mere velocity. The strengths of the absorption lines serve as a sensitive thermometer, since which atoms are ionized and which are excited is governed by the temperature, and this is the physical basis of the familiar sequence of stellar classification running from the hot blue stars to the cool red ones, which is at bottom a sequence in temperature. Once the temperature and gravity are fixed, the depths of the lines then measure the chemical abundances, element by element, the very technique that revealed the chemical history of our galaxy. And the shapes of the lines carry still more, for thermal motion broadens them, the pressure of a dense atmosphere broadens them further and so distinguishes dwarf stars from giants, rotation smears them out, and a magnetic field splits them in two. A single high-resolution stellar spectrum therefore yields the temperature, the gravity, the composition, the rotation, the magnetic field and the velocity of a star all at once, which is why spectroscopy, more than any other technique, turned astronomy into astrophysics. Because any motion along the line of sight shifts the wavelengths of the spectral lines, spectroscopy is also a precise measurer of velocity. The fractional shift of the wavelengths, the redshift, is equal to the line-of-sight velocity divided by the speed of light, a shift to the red for recession and to the blue for approach, and at cosmological distances that redshift is reinterpreted not as a local motion, but as the stretching of the wavelength by the expansion of space itself, the measurement by which Hubble established that the universe is expanding, and by which modern surveys map its structure in 3 dimensions. The same effect underlies the radial-velocity method of finding planets, in which a star's small answering wobble about its shared center of mass with an unseen planet shifts its lines back and forth. That wobble is tiny, only about 12 meters per second for the Sun and Jupiter, and a mere 9 centimeters per second for an Earth in the habitable zone, and it can be caught at all only because thousands of lines are cross-correlated together, and the spectrograph is stabilized to an extraordinary degree. The chief obstacle now is no longer the instrument but the restless surface of the star itself, whose spots and churning produce false velocity signals that must be carefully modeled away. Astrometry is the precise measurement of the positions and the motions of celestial objects, and it furnishes the one direct, geometric rung at the base of the whole cosmic distance ladder. 2 motions are measured. Proper motion is the slow angular drift of a star across the sky, the reflection of its true sideways velocity relative to the Sun, and trigonometric parallax is the small yearly ellipse that a nearby star seems to trace as the Earth swings around its orbit. The parsec, the fundamental unit of astronomical distance, is defined as the distance at which one Earth-Sun radius would subtend an angle of a single arcsecond, which yields the beautifully simple rule that a star's distance in parsecs is just 1 divided by its parallax in arcseconds. A star 1 parsec away has a parallax of 1 arcsecond, a star 100 parsecs away, a parallax of 100th of an arcsecond. 1 parsec is about 3¼ light-years, and the nearest star, Proxima Centauri, lies about 1 1/3 parsecs off. Because the distance is the reciprocal of the parallax, the fractional error in the distance equals the fractional error in the parallax, and this single fact governs how far the method can reach, for a fixed angular uncertainty yields ever larger relative errors as stars grow more distant and their parallaxes shrink toward it, until beyond some point the parallaxes become little more than upper limits. This is why the leap from milliarcsecond to microarcsecond precision was so transformative. The first stellar parallax was measured by Friedrich Bessel in 1838. The European Hipparcos mission reached milliarcsecond precision for about 100,000 stars, and its successor, the Gaia mission, launched in 2013, revolutionized the field by working at the microarcsecond level, a precision akin to measuring the width of a human hair seen from 1,000 kilometers away. Gaia has fixed the positions, the motions and the brightnesses of more than 1.5 billion stars, carrying trustworthy geometric distances out across much of the Milky Way, and recalibrating the entire ladder of cosmic distance that rests upon them. Even a perfect telescope, though, cannot form an infinitely sharp image, for the diffraction of light by its finite aperture sets a hard limit. 2 points of light are just resolvable when their separation matches the radius of the first dark ring of the diffraction pattern, an angle that shrinks in proportion to the wavelength, divided by the diameter of the aperture. For a 10-meter telescope working in visible light, this diffraction limit is about 100th of an arcsecond, and it improves with a larger aperture and a shorter wavelength, which is the reason that ever greater telescopes and instruments working at ever shorter wavelengths are pursued for the sharpest imaging. From the ground, however, the atmosphere usually prevents any telescope larger than a few tens of centimeters from ever reaching its diffraction limit. The turbulent mixing of air at different temperatures distorts the incoming wavefront, an effect called seeing, whose strength is captured by the fried parameter, the width of aperture over which the distortion of the wavefront amounts to about one wavelength, typically 10 to 20 centimeters at a good site. The consequence is striking, for the atmosphere then acts as though it were itself an aperture of only that small size, so that the seeing limited resolution is set by the wavelength divided by the fried parameter, quite independent of the telescope's true size. A 10-meter telescope and a 20-centimeter one at the same site deliver, in a long exposure, exactly the same sharpness of image, somewhere around 0.5 to 1.5 arcseconds. The giant telescope wins not in resolution, but in the light it gathers and the faintness it can reach. Seeing is milder at longer wavelengths, which is one reason infrared observing can more readily approach the diffraction limit. Beyond blurring the image, the atmosphere also dims and reddens the starlight, and the loss grows with the length of the path the light must travel through the air, a quantity captured by the air mass, which is one at the zenith and larger toward the horizon. The dimming obeys Bouguer's law discovered around 1670. Expressed in magnitudes, the light lost is simply the air mass multiplied by an extinction coefficient for the band in use. A star 60 degrees from the zenith is seen through twice the air, and at a typical coefficient, appears about a third of a magnitude. Fainter, near the horizon the dimming climbs past a full magnitude, which is why precise photometry is kept to air masses below about 2. The calibration of photometry solves at once for both the extinction and the instrumental 0 point, by observing standard stars across a range of air masses. The three physical culprits are the scattering by air molecules, which reddens the transmitted light, and is the very same physics that paints the sky blue and the sunset red, the scattering by dust and haze, and the molecular absorption by ozone in the ultraviolet, and by water vapor in the infrared. The atmosphere bends the light too, through refraction, lifting the apparent position of an object, so that a star on the horizon appears about 0.5 degree higher than it truly stands, and because the bending depends on wavelength, smearing the star into a tiny spectrum that must be corrected in exact work. Most decisively of all, the atmosphere is simply opaque across most of the spectrum, transmitting only through two great windows, the optical and near-infrared and the radio. The ultraviolet is absorbed by ozone, most of the infrared by water and carbon dioxide, and the X-rays and gamma rays by the bulk of the air. This opacity is the fundamental reason for space-based astronomy, and the Hubble telescope, the Chandra X-ray Observatory, the James Webb Telescope and many others were launched precisely to reach the wavelengths and the sharpness that the ground can never provide. All these fundamentals combine to set the limits of what any observation can achieve. The limiting magnitude deepens with the aperture, with the integration time, and with darker and steadier skies, but only so far before three walls are met. There is the noise wall, beyond which reaching the very faintest sources grows prohibitively expensive in telescope time. There is the confusion limit, where the faint objects begin to blend together within the instrument's beam and cannot be separated no matter how long one integrates. And there is the atmospheric wall, where seeing caps the resolution regardless of the telescope's size. Adaptive optics was developed to defeat that last wall. A system measures the distorted wavefront many hundreds of times each second and applies an equal and opposite correction with a deformable mirror, its surface reshaped by thousands of tiny actuators at kilohertz speeds, fast enough to restore a near-perfect image on the largest telescopes. Because a naturally bright reference star is rarely at hand, modern systems conjure an artificial one by shining a laser to make sodium atoms glow high in the atmosphere, and it was adaptive optics that made possible the decades-long tracking of the stars orbiting the black hole at the center of the Milky Way, work honored with a Nobel Prize. A distinct but equally fundamental limit governs time-domain photometry, whose aim is to catch a small change in a star's brightness rather than to fix its absolute level. Here differential photometry, measuring the target against comparison stars on the very same frame, cancels most of the atmospheric and instrumental variation, so that the precision is set largely by the photon shot noise alone. The benchmark case is the transit method of finding planets. A planet crossing the face of its star dims it by the ratio of their areas, about 1% for a Jupiter, easily seen from the ground, but only some 84 parts in a million for an Earth, a dip so shallow it demands the photon-limited steadiness of space. The same fundamentals underpin the study of variable stars, of astrocosmology, and of the fast-growing field of transient astronomy, in which wide-field surveys sweep the sky again and again to catch supernova and the optical flashes that accompany gravitational wave events, turning astronomy from a static map into a moving picture of a changing sky. The ultimate escape from every atmospheric limit is to leave the atmosphere altogether, and so the frontier of faint, sharp, many-wavelength astronomy is now shared between the giant ground-based telescopes with their adaptive optics and the observatories in space. And the deepest questions that this whole chain of measurement feeds, the disputed value of the expansion rate of the universe, the so-called Hubble tension, and the true natures of dark matter and dark energy, remain genuinely open, their resolution depending directly upon the continued refinement of the very photometric, spectroscopic and astrometric fundamentals set out here.